Let's wait a few more seconds and we will start on time. Uh, I can really start introducing myself. My name is Mario Fusco and I work for Red Hat. I'm the project lead of Drules, which is the rule engine of Red Hat, which will be also part of this presentation. And I'm here with my colleague Nicole, and she will do the second part of this talk as well. We work together on the same project. Okay. So I don't know if you know me, but if you don't, it is because last time I was supposed to give the keynote here, and then of course I had COVID that week. So and okay, so I had luckily a second chance to talk here, and I hope you will enjoy this. Okay, so I'm here to speak about machine learning, of course, because why not these days? But under probably a little different point of view as usual. Okay, so I'm speaking about machine learning indeed, but my point is that we can probably complement this technology with other stuff in order to make it better. What is machine learning? My first machine learning is basically a bunch of are statistical tools, and it's also the thing that if you try to buy a dishwasher or a washer on Amazon, Amazon will think that you will about to open a new laundry because it will suggest you to buy 3 more washer. Just because they are statistically related, right? You probably don't need for washer in your rooms, but this is how machine learning generally works. And before moving forward, I also wanted to clarify a bit the terminology. We are using these days to use artificial intelligence and machine learning terms, and also probably deep learning in an interchangeable way. But this is not the case. They are two really different things, or three really different things. One is a subset of the other, and probably to better understand each other, it's time to finally start using the right terminology. So, artificial intelligence is everything, is every software that tries to mimic human behavior. Okay, this software may be driven by a knowledge base, a rule base, or can learn by itself uh, how to do this. And only in this second case, so it's a subset, only if it learns by itself how to do this, we speak about machine learning. And then deep learning, like LLM, or other technique of the machine learning area that basically are machine learning on steroid, meaning that you have other algorithms to let the machine to learn really complex stuff. And this talk is not only about machine learning, as I said, but also about my main project, which is a rule engine. But the rule engine is things of the 80s, so we don't like it anymore. Now it's just a little bit more polite to call it a production system, but if you want to be really, really cool, you call it symbolic artificial intelligence. And now, out of the blue, we are still allowed to bring this technology back from the 80s and make it modern again. Okay, so let's call this a symbolic artificial intelligence just because we are the cool guys. But why really you want to do this? Because as I said, machine learning, it's a bunch of statistical algorithms that basically learn your business. So in the example that I made before, the the 3 washer was statistically related, and then Amazon suggested you to buy the 3 of them in a bundle. But this is not how it actually works, right? And why this is happening? Because you should mix this statistical knowledge with the actual knowledge of your business. So you should mix what we call proper machine learning, which is made of these statistical tools with neural network and stuff like this, with another kind maybe of artificial intelligence with our rule engine. So and if you think about it, inside the rule engine, inside the knowledge base that you code inside the rule engine, there it lies the knowledge of your domain. So yes, you can make it the machine learning to rediscover it again, probably in a good way or in a bad one. But why should you so? I mean, you already have the knowledge of your domain. Very likely in your domain, if a customer is buying a washer today, is not or a phone today, it's not about to buy a second phone or a second washer tomorrow. So it's pointless to suggest it. Okay, and this is really part of your knowledge of the knowledge of the domain. So you can really encode this stuff in your program. And there is a bunch of research about mixing these two technologies, which is called neurosymbolic AI. If you look about it, you can find a lot of paper and discussion and example about this. And in reality, there are a few of already well-proved pattern on how you want to mix this stuff. And I will give you, for instance, an example later of the latest possibility listed here, which is mixing not ChatGPT, but an LLM with rules to see how to complement each other in a practical example. Okay, and this practical example has been inspired by something that happened a couple of months ago. I don't know if you heard about this news. Basically, what happened is that a customer of Air Canada was chatting with a chatbot of the company on the website, and this chatbot was made with an LLM. And at some point, the LLM totally hallucinated and told to the customer that he was entitled to have refund of 650 Canadian dollars. Okay, but this is totally invented. I mean, he mentioned it a refund policy of the company, but the refund policy doesn't exist at all. It was a total hallucination. Okay, so what happened is that the customer asked, okay, your bot told me that you owe me some money, so give me my money. Of course, Air Canada refused to pay because he said this is not really our refund policy. The fact is that, of course, the customer takes screenshot of the chatbot conversation. He went to a judge, and the judge gave him right, and Air Canada was forced to pay the refund that the LLM invented totally out of the blue. Okay, so this is a really thing. I mean, hallucination are a real problem. I took this screenshot yesterday or 2 days ago at most, where, yeah, even the CEO of Google admit that there is no solution for hallucination. He call it a feature of the LLM. Well, maybe it's a feature, but probably not the one that you really want. And the question remains if how we can compensate this problem. Okay, and the solution that I'm suggesting here it is to use a proper rule engine. And in reality, there are academic paper already mathematically demonstrating that hallucination are not avoidable. It's part of how this thing work, and you cannot do anything about this, right? And if you think about it, you don't want your chatbot to hallucinate and grant people a refund that they don't really deserve, or you don't want it to hallucinate and decide if somebody is eligible or not to get a mortgage or stuff like this. just because it decides so. Also, all this stuff typically cannot be a black box. It has to be auditable. It has to be trackable. If you refuse, if your bank refuse you a mortgage, they have to tell you why. It's not, and of course, the LLM say so. It's not an actual justification. Okay, so what I try to do with my experiment, I say, as I said, I took inspiration of that news about the Air Canada chatbot, and I try to replicate the same situation in a proof of concept. So what I'm doing is that I'm using an LLM to collect the data of the customer. But once I have the end of the flight of the customer, but once I have this data, I send them to Druze to be in order to allow Druze to proper calculate the actual refund amount he found using the knowledge business of the airline company. Okay, and I also used the Druze for a second purpose here. As I said, this LL, the goal of this as LLM is collected in a human-friendly way the data of the customer. So I'm using Druze also as a state machine. So this application goes through three states. The first state is collecting the data of the customer, and then you have a second state when you collect the data of the flight and the eventual delay or the other problem that he had. And then when this information gathering process is complete, then you send all this information to the rule engine, which calculates the correct refund amount to you for you. Okay, so I have this application made with Quarkus and a couple of extensions. I'm using the LangChain4Chain extension for the LLM interaction, and I'm using the rules extension for the rule engine interaction. Okay, let's give a run to this. So now I'm launching this web application. In reality, as you will see, if you will go to the project, you will see that I collected a few examples about this interaction between an LLM and a rule engine. I'm showing you just one of them. Okay, so if you go here, you see, I mean, I have three examples at the moment. I'm about to show you this one. So here I have a functional chatbot for that airline refund policy. So let's start chatting with our chatbot as AI. So on this, you can immediately notice two things. The first thing is that I suck at create web interfaces. That's not something really new for who knows me. And the second thing is that it takes ages to reply. The reason is it is because I configured this application to also run the LLM on my machine. So everything is local now. The LLM is running on my machine, and this web application is running on my machine. Okay, but the computational cost of this web application is negligible compared to the LLM one. Okay, so here, as you can see, I told you that this application those three states. Okay, it's actually state machine. We are in the first state. It's asking me, okay, what is my full name? So it's asking the data about the customer. It's asking me what is my name, basically, and my age. Okay, I will provide only my name for now. And yes, you can see, let's see what's going on here while the LLM is doing his stuff. What I'm doing here now is that I'm using this service that is provided by the Chain4j integration. As you can see, I just created this interface and annotated it. I didn't write any actual class. The class is automatically generated for you at build time, and this class creates communication between your program and the LLM. Okay, so what this thing is doing is sending the text that you are writing to the LLM and ask to the LLM to extract the customer data in this case. And as you can see, it returns a proper customer object. Okay. So what the Quarkus Chain4j integration does is it introspect this object. It see which are the fields of this object. So the customer object is made of a first and last name and the age, and it creates a string that say, okay, extract to this string, which are the two things that I sent to the LLM so far. Extract this customer, the data of the customer. Okay. The fact is that, okay, now it's saying hello Mario, but there is still something missing on the customer because it doesn't have my age yet. So it's asking now for my age. I will say that I'm 70. You will see why later. So the customer data at this moment are still incomplete because it's missing the age. So we are still in the first state of the state machine. Okay, it's still using the customer extractor. At this point, it should have all the available data from the customer, and it should be able to extract the information about this customer. So let me also show you in the meanwhile the state machine. Okay, so I put all the data of this interaction in this object session data. So the state machine is written with the 3 rules, but it's very simple. If I don't have the customer yet, then I'm in the extract customer state. Otherwise, if I have the customer but not the flight, I am in the extract flight state. And otherwise, I have all the data, and then I'm finally ready to calculate the refund. Okay, this thing is still doing something, but it should. As you can see, it already extracted the proper data of the customer from this interaction. So the LLM returned a well-formatted JSON with my first name, my last name, and my age. And at this point, at this point, the customer data are complete. We are transitioning in the second state of the state machine, and this thing now is asking me for the information on my flight. Okay, I will say that I was on flight 22, and it had 4 hours of delay. Okay, so from this string, it should be also able to extract the data of the flight. Of course, this is not always true. The problem of doing a live demo with an LLM is that you never know what is going to happen. You never know if it is going to work or not. And it did yet is not working now. Let's see why. Okay, so the reason why it's not working this time, it almost, okay, just to be clear, I'm using an LLM model on my machine. It's called a Mistral 7B model, but it's very it's a tiny model, of course. Otherwise, I wouldn't be able to run on my machine, so it's not always precise. The problem now is that I send this information to the data extractor of the LLM. The problem is that the LLM, if you see, it replied with this JSON, and all the information are okay. Problem is the LLM hallucinated in this case and decided to put a comment inside the JSON, and of course this make the JSON unparsable. So and then I get this exception. So this thing sometimes happens, sometimes doesn't. Let's try to give it a second spin, but yeah, uh, the problem is that you never know what happens with when you play with LLM. But again, uh, typically this thing works. The main problem is that I'm using a toy LLM model just because I wanted to make it run on my machine. So let's see what if it's going, if it's able to do this. Anyway, what we expect here is that I told him that I had 4 hours of delay, which are 240 minutes, and my rule, this is not an hallucination now. This is the knowledge base, the actual refund policy of the airline company that is coded inside the rules rule. Okay, so this refund policy say that you are entitled of a refund of $2 for each minute of delay. And if you are a senior, if your age is bigger than 65, you are entitled for a 10% more. This is what is saying. So what we expect is that we have 240 minutes of delay, which are for $180 plus the 1%. Since I said that I'm 70, it should be $528. Of course, this got that exception, so it's not working anymore. Uh, but but of course, I took a screenshot of a successful iteration just because I know that sometimes it works and sometimes it doesn't. I cannot do much about this. Anyway, this should solve the problem of having a reliable application that calculates the eventual refund. Again, the problem is only the poor LLM model that I'm using. Don't know what's going on here anymore, but okay, I don't want to waste time on this, to be honest. And okay, this is just an example, but of course I went one level up. I went up meta one level, and I asked to ChatGPT, okay, tell me what are other good use cases to combine your capabilities with a rule engine. And as you can see, ChatGPT actually listed a lot of them, which are, of course, the chatbots, having a chat that does for you some personalized recommendation, that schedule appointment, something for financial services. There are a lot of use cases, and now, in reality, I'm in contact with a professor of the University of Utrecht these days, and we are playing together for a system that combine an LLM with rules in order to provide advices about cybersecurity. So there are a lot of nice use cases for this idea. So just to recap now, machine learning is a new paradigm, or relatively new. Um and what's the difference between this and the rule engine? With the rule engine, you feed the rule engine with the data and with the rules, and you get answers. Okay. Typically, what happens with the machine learning system is something different. You you fed him, you train it with answers and data, and then you obtain rules, obtain a behavior. Okay, so these are the difference between the two approaches between rule engine and machine learning. And if reality, these two things are really complementary. So the other idea would be to short circuit this diagram and feed the rules generated by the machine learning to the rule engine and possibly do the opposite. And this is the topic that Nicole covered, and I will leave the stage to her.
So on one hand, we have, let's say, a rule engine that is fast and reliable. It's interpretable, effective with well-structured problems, but it's not scalable and lacks of adaptability. And on the other hand, we have machine learning that is highly adaptable and flexible, can handle complex and vast amounts of data. We can do automatic rule extraction, but lacks of interpretability and depends on data. So the idea is to integrate machine learning with rule engine in a hybrid AI approach, leveraging their strengths and overcoming their weaknesses. To explore this idea, we use rules for the symbolic AI part of this solution, and we introduced a machine learning process to automate the knowledge based creation from data, which we can also execute using and domain knowledge as well. There is a combination data and existing knowledge base. So in general, a hybrid AI approach gives us a more versatile AI system that can efficiently handle complex scenarios, adjust to changing conditions, and improve performance and accuracy. Now, the machine learning process that we have introduced consists of two basic steps. Thank you. So, at the beginning, we want to initialize the knowledge base with a compact set of decision rules to fully cover the instances we have in a data set. This means that at the end of the first step, we want every data point in a data set to be supported by the knowledge base. And then at the second step, we want to identify the rules that are erroneous to support some data and fix these rules with some additional rules, which I will explain in a while. We use the revised version of the 1R algorithm to learn these decision rules from data. Now, the 1R algorithm is a simple but yet accurate classification algorithm that generates one rule for each predictor of feature that we have in a data set, and then selects the rule with the smallest total error as its one rule. In the revised version that we have implemented, the rule with the highest accuracy and highest coverage is selected. We have introduced a score metric as the product of the accuracy and coverage of the rule to ease this selection. And now we will see an example. Here we have a data set with 4 features: outlook, temperature, humidity, and wind. And we want to suggest if it's a good idea to play tennis or not. Now, the 1R algorithm constructs frequency tables for each predictor against the target variable. In our case, is the play column. Okay, and for each predictor, it goes through the conditions. It goes through the values of the predictor to construct conditions. For example, if outlook is equal to sunny, still a problem. Now you can hear me better? Okay, great. So let's go again. For each frequency in the table, that is outlook, temperature, humidity, and wind, we want to explore all values of the features, construct conditions. For example, if outlook is equal to sunny, outlook is equal to overcast or rain, and assess these conditions to find a good decision rule for a particular target class, that is the yes and no in our case. So as example, for the outlook feature, we have 3 values: sunny, overcast, and rain. When outlook is equal to sunny, we can see that this condition supports 3 cases that fall in the yes class and 2 cases in the no class. When Outlook is equal to overcast, then we have 4 instances in the yes class. And when Outlook is equal to rain, we have 2 instances in the yes class and 3 in the no. Then we use this to construct rules as follows. The rule for deciding a rule, we will select the class, the most important class for each. So for example, for Outlook equals to sunny, we will say that if equals to sunny, then place equal to yes. If Outlook is equal to overcast, then place equal to yes. And if Outlook is equal to rain, then place equal to no. For each decision rule, we calculate its coverage and accuracy and the score. And we select the one with the highest score as a good predictor for the particular class. Now back to our machine learning process, just to show you briefly the flowchart. We start with an empty set of rules. During our first step, we iteratively learn rules until we end up with a compact set of rules that fully covers our data. And then we go to the second step, and iteratively we identify rules that erroneously supports our data, and we find a new rule for this subset of data to try to fix the problem we found. And we'll see an example just in a second. So to show an example, we use a database from Google, a dataset for the early stage detection of diabetes. This dataset has 15 features, but to simplify our demo here, we use the most frequent ones, the most important ones, polyuria, polydipsia, and gender. And we also filtered our data, we restricted our data to the middle age group. Our target is to predict a positive or negative diabetes. So the first step of our machine learning process identified these rules. So the initial version of the knowledge base consists of these rules. The first one says that when polydipsia is yes, then the prediction should be positive, and when polydipsia is no, the prediction should be negative. Now these 2 rules together cover the entire data points that we have in the data set. We have coverage 100%, but 28 instances of the data, they are erroneously supported, okay? And we want to fix these errors. To fix this error, we find this additional rule, which it's like a defeater of rule 1. It comes to fix rule 1, and it says that when polydipsia is no, but also when gender equals to 50, then the prediction is positive. And that way, we reduce the number of errors to 17. And that way, we repeat the process, trying to eliminate all the errors. Of course, we have to add more features to this particular problem to make it right. But this was just to show you an idea of how this process works. Now, to conclude, machine learning is just a fraction of the whole AI story. The general goal of AI is to mimic the human behavior. There are many ways to achieve this goal. Letting the machine learning from data is just one of them. It is important to say that machine learning will not replace symbolic reasoning or symbolic AI. They are complementary technologies. Machine learning and symbolic reasoning are different technologies with their own pros and cons, but together, often both the flexibility and human friendliness of machine learning and the strictness of transparency of symbolic reasoning are required. Intelligent application, you can leverage and integrate the strengths of both. So here, the first 2 links are links to our projects if you want to go and give a look, and then some references that we used for this idea we just presented to you. Thank you.